So let me continue with a lecture from yesterday. So yesterday we derived the equations for the random phase approximation. So we derive the main quantity. Let me put it in. Okay. Okay, so we derive this explicit expression for the polarization using the time-dependent perturbation theory. So yesterday, Vijay taught us about Green's function and self-energy. So I thought it could be good also to derive the same equation, the RPA equation, using the Green's function approach. So this is what we are going to do in a moment. Let me see. Okay. So let me first define the Green's function. So this is a zero temperature Green's function, not a temperature dependent Green's function. In the interaction picture, so this was introduced by Schwinger, I think, where we include a perturbing potential. This phi is as external potential, which can be time dependent. And the Green's function then has the following form here. So we have a time ordering operator, the T, and this state phi 0 is the exact ground state of the Hamiltonian. It's interacting many-body Hamiltonian. And this S operator here is just the time development operator from minus infinity to infinity in time. I did not write the minus infinities because I assume that if when you write an integral like this, it means for the whole time and space. So in this representation, the field phi, this field phi here is in the interaction picture. So as we saw yesterday, this field is then independent of the phi. So that is an important point, that the field is independent of the phi, and it is defined in this way. So it's just a unitary transformation from the original Schrödinger operator into the interaction field operator. So we can see that it does not depend on the external field phi. So with this Green's function, it is quite easy to calculate many quantities. For example, if we want to calculate the response functions, all we have to do is just take functional derivative of the density with respect to the field. That's the definition of the response function, linear response function. And we just use the expression for the density in terms of the Green's function. So this is, the density is then just a diagonal component of the Green's function. And then we take the functional derivative and calculate it at phi equal to 0. So in this representation, this field here is a kind of mathematical tool for calculating response functions. We never actually need to know this field phi. So because we always set this phi to 0 after we do the calculation. So after doing this derivative, we set the phi equal to 0. So all we have to do is now to calculate this expression here. So I just use the GM. So the main thing to calculate is then this derivative of this S with respect to the field, because all other quantities are independent of the phi. So all the field operators here, are independent of the phi. So all we need to know is how this quantity looks like. So I just take the functional derivative of this S with respect to phi. So this is an exponential, so it will bring down the density operator. And we don't need to worry about the order of this S and the density operator, because we have a time ordering operator. And also we don't need to worry about the sign, because the density operator consists of two field operators. So if we interchange anything with that, it does not change the sign. We have two field operators. So this is basically what we have. And we calculate this at phi equal to 0. So that gives me minus I times the field operator. So it's quite simple. And then we just plug it in here, and we get this expression. So the first one comes from the numerator, and the second one from the denominator. And we get the Kubo formula, and we could rewrite it in terms of the density fluctuation operator, and we get the Kubo formula. So we get the Kubo formula basically in just one or two lines using this Green's function approach in the interaction picture. So we just can do a little exercise here to show that this is the same as this one here. So this is the time-ordered response function, which is related to the retarded response functions. So we can always obtain the physical response function from this time-ordered response functions. So the real parts are usually the same, but the imaginary part may have different sign depending on whether you are in negative frequency or positive frequency. But you could always get one from the other. So I have some notes here. So I will have this lecture, these slides on the web. So I probably do not need to go through this. I just want to show that this definition of the Green's function in the interaction representation here is equivalent to the usual definition of the Green's functions using the Heisenberg operator. But let me just skip this thing. And then you could also get the spectral representations of the response function simply by using the usual procedure of inserting a complete set of eigenstates of the Hamiltonian in between the density fluctuation operators here, and then do Fourier transform, like what we did yesterday in the lecture of Vijay. So the linear response function actually contains an important information about the system. It contains the poles of this response functions, this pole here, as actually gives us the exact excitation energies of the interacting n-electron system. It's an important property. So if we plot this, the imaginary part of this response functions, we usually see some peaks, and those peaks correspond to the excitation of the system. And in the many-body system, many electron system, we might have some collective excitations, and you will see these collective excitations as peaks in the imaginary part of the response functions. For example, yeah?
What is delta rho?
Delta rho is the difference between the density operator and the density. So this is a number, this is an operator. Okay. It's a fluctuation. Okay. So now we would like to derive the random phase approximation from Green's function. So get a more general picture. So again, we start from this definition of linear response functions as a functional derivative of the density with respect to the applied field. And again, we write it in terms of the Green's function, like that. So now we use identity. So G times its inverse is equal to 1. So 1 here can mean a delta function depending on your basis. Yes. And if we take the functional derivative of this equation, then we get two terms, one from the G, this one here, and then one from the G minus 1. But this is a constant, so that's the right-hand side is equal to 0. And so we get an expression for this dg d phi in terms of the Green's function and the derivative of the inverse Green's function with respect to the field. So the reason that we rewrite it in this form is because it's much easier to calculate this derivative here than the original derivative. We look at the equation of motion. So let me go slowly. So yesterday, Vijay told us about equation of motion of the Green's function like this. This is a more general form, and you have this one particle part here, and this is the self-energy. Otherwise, it's the same. So then the inverse is given by this expression here. So now we can easily take functional derivative of this quantity here, because these are all we have here. So when we do that, we get three terms. So this does not depend on the phi, on the field. This one does not depend on the field either, because these are just the kinetic energy plus the external potential. It's fixed potential from the nuclei, for example. So they do not depend on the perturbation phi. And then we get one here from the phi. And we get two additional contributions, one from the variations of the Hartree potential with respect to the field. And in addition, the self-energy also changes when we apply an external field. So we have these two terms. Yeah. Now, so we go back now to the to the response function here. And all we have to do is just use this expression here and plug in this result into that one, and we get the following result. So this is the original expression, dg d phi, and we write it in terms of the inverse Green's function. And we know this quantity here, and we just plug it in. So this is what we have for the response function. Yeah. So I have written everything here in the schematic way, but it's quite easy to put in the variables at the end. Yeah. So now in the Hartree approximation and in the random phase approximation, what we do is we neglect the self-energy, the variation of the self-energy with respect to the field. So that is why sometimes we call the random phase approximation as a time-dependent Hartree, because we only consider the change in the Hartree potential when we look at the response function here. So this is set to 0. So actually this is sometimes called the vertex corrections. And we get then this expression for the response function in terms of the Green's function. So this is the reason that why random phase approximation is equivalent to time-dependent R3. Yeah. Sorry, didn't get.
What is the justification for taking delta sigma delta phi is equal to 0?
Well, it's not really. I mean, I would say that quite a lot of the effects of the external field on the system is contained in the R3 potential already. So this is like the change in the exchange correlations with respect to the applied field. So it is an approximation, but it has been found to be quite good in many systems. So this is not exact, of course, but it is an approximation. This is what we approximate for the response functions. And so this is the vertex corrections, usually called. And it can be important in some cases. So for example, if you want to study excitons, it's necessary to take into account this term here, because this gives the particle-hole interactions in the polarizations. Whereas if you don't include this term, then you only have polarizations of non-interacting like polarizations. There is no interaction between the particle-hole. So it's not perfect, but this is what we do in the random phase approximations. So now we can put in the variables 1 and 2. So 1 here means position and time. So I just write down everything like what we had before. So we have this equation here, and I just plug in I just put in all the variables in here. So now I can rewrite this the change in the R3 potential with respect to the field, because we know that the R3 potential is just V times the density integrated over this 4 variable. And this, by definition, is the response function. So then we get an integral equation for the response function. And we could also define what we call the polarization function, which is a product of 2 Green's function. So if you like diagrams, and it is just this bubble. So coming back to the question before, so if you so in the RPA we only have a bubble like this, but if you take into account the self energy also, then you might have interaction between this is the particle and the hole here, so you might have interaction between them that you might need if you want to describe excitonic effects, for example, and other quantities. So if we write it in terms of this P, then this equation becomes just like what we had before, the RPA. So actually the form of this equation is exact. Even for the exact response function, we have the same equations. So the difference, it really comes from this P here. So in the case of the exact response functions, this polarization function will contain a vertex correction. So there will be some interactions between these 2 lines here. But in the case of RPA, we only have just a bubble. So the RPA, in the sense, is in this point of view, is a little bit more general, because this Green's function doesn't have to be a non-interacting Green's function. It can be interacting Green's functions. It's just that the polarization is given by the product of the two Green's function. So that's if you write it in terms of diagrams, and you have this bubble diagrams. As you can see that if you iterate this, you get a set of bubbles with 1 Coulomb interaction, 2 Coulomb interactions, and so on. That's the well-known RPA response functions. So maybe I should ask if there are any questions. I guess everything is okay. So I can continue. So, so the main quantity here is is the P again, and we could show that this P is exactly the same as what we had before if we put in the non-interacting Green's function into the G. So I would do Fourier transform. So this Fourier transform then becomes a convolution in the frequency space, because we have a product of two Green's function in time space, so then it becomes a convolution. And if it use non-interacting Green's function in this expression here, then we obtain the expressions that we had before. It's exactly the same. So this is the main expressions. The main quantity that we need to calculate the Hubbard U. So let me skip this thing here. Yeah. So I just want to remind you what the kind of materials that we are interested in. So this is a typical electronic structure of correlated materials, usually with partially filled narrow band of 3D or 4F origins at a Fermi level crossing this standstill state here. So this is an example of a perovskite, transition metal perovskite. This is very much studied in the literature. You can find many papers on this. Because this is a very simple structure, it's a simple cubic structure. And this typical electronic structure is like this. So you have a narrow band crossing the Fermi level. In this case, this will be the T2G, the T2G of the 3D coming from the vanadium atom. And then you have the oxygen P here and the strontium 4D. So we would like to usually then know the Hubbard U for the electrons residing in this narrow band. That's our aim. We would like to renormalize the Coulomb interactions so that we can have just a model for this narrow band. We want to downfold the effects of the other bands. This is the completely occupied and the completely unfilled bands, and have the effect of these bands here onto this narrow band. That's our aim. So the way we do this is, so we first, so this is a schematic picture then of the densitive state or the band structure of these correlated materials. So we have these narrow bands, partially filled narrow bands, and this is could be the oxygen band, for example, and this is some other unfilled bands up here. So we divide the polarizations into two parts. So first of all, we divide the one particle Hilbert space into two parts, what they call the D subspace, which is the subspace corresponding to the Hubbard Hamiltonian or the model Hamiltonian. This is my D subspace here. And then the rest of the subspace, we call it R, so the R subspace here. So that is clear. So now we also divide the polarizations into two parts, what they call the PD. So the PD here is the polarizations within the model, D subspace, PD, and the PR. So it's a little bit confusing, maybe the notation here, because PR means just the rest of the polarization. So the difference between the true polarizations and the PD. So it should not be confused as meaning the polarization within the R subspace, because this PR actually contains also mixing between the D and the R. For example, here we could see that the PR contains transitions from the R subspace to the D, and also here from the D to the R. So not only from R to R, but also has contributions from D to R. So maybe I should have been called P-rest here rather than PR. But anyway, that's how it is defined here. So the division, I think it's quite clear. So now we start to derive the effective interactions just for the electrons residing in the D subspace is what we would like to do. So we start with a fully screened interaction. We have derived this in the previous lecture. Screen interaction is equal to the bare one plus VPW. So these are the screening potential. So we can solve this. So we have to remember that it's a matrix, it's not a number, it's just matrix, and these quantities are frequency dependent. So this is true for each frequency, and they are matrices. So I can just solve this. It's very easy. I just put this term to the left hand side, and then I can take out the W, and we have this inverse of 1 minus VP. That's a straightforward algebra. And so now I do a little bit of trick. I insert a unit matrix here. So 1 minus VPR. That's 1 minus VP of the inverse. So nothing happens. It's just 1 here. And then we use the matrix property. Then if you multiply two matrices A and B and take the inverse, that's equivalent to the inverse of B and the inverse of A. So I use it here. I use that formula for these two terms here. So then it becomes the inverse of this times, this one times that one, the inverse. Yes. So this thing is equal to that one if we use that formula. Straightforward. So I can just write out the P. So the P is just the sum of PR and PD. So everything else is the same. And now I can multiply this and that one, so that gives me 1. And then I have this one times that one, so give me this thing here. And this thing remains as it is. So it's just a straightforward manipulations of matrices. So now we notice that these two terms are the same. It's the same quantity here. So we call this WR. So now we see that, so we have an equation now for W. So this is the original equation. So this equation cannot be rewritten in terms of PD, which is the polarizations, just for the model, and this WR. So this WR is partially screened Coulomb interactions, because I only have a PR here. So this is the original expression with the full P, and here I only have a PR. So this is a partially screened interaction. which we can interpret this as a Hubbard U, quotation mark, because now everything is a frequency dependent quantity. So we can interpret this as a Hubbard U because this is the fully screened interaction, and when it is screened by just the PD, so the polarization within the model, we get back the fully screened interaction W. So we can think of this then as the effective interactions of the model. And all these quantities now is a function of frequency also. It's not just static, but frequency dependent U. Yeah.
You started with the Hubbard model?
Yeah, so actually this quantity here, you can calculate this as a function of positions of R and R prime. So, and then it depends, it's really up to you how you want to use that quantity. So if you just want to keep the on-site interactions, then you just calculate the matrix elements of this in some localized orbitals and keep the on-site term. But in principle, you can calculate also intersite terms, as many as you like. So this is quantities which depends on the positions R and R prime, and you can calculate anything. So you get the full matrix of the Hubbard U, because you can take any matrix elements. It's a question of.
Hubbard U in general is considered some kind of, say, intra-orbital or inter-orbital. At least not a non-local that length,
yeah,
right?
Yeah. So in that sense, you just take the local term, the on-site term. Yeah. So I'm just rewriting this. So this is an equation done for the U. So I call WR now U. You get the same equation as this one, but with a PR instead of P. So in practice, what we do is we consider, for the full system, you have this expression here. I'm a little bit lazy here. I'll just make a shorthand notation here. So this is the full expressions, the sum over all possible occupied and unoccupied states is apparent. And we have exactly the same expressions, but the states is restricted to the D subspace. It's D subspace is the model. And then you can just calculate the difference between these and this. Or we could also calculate this explicitly. Yeah, does not matter. And then we solve these equations. So this is in R and R prime, function of frequency. It's an integral equation for du. And of course, when we solve these equations, we usually use basis functions. But those basis functions are just mathematical basis functions. You can use plane waves, or you can use localized orbitals, anything you like. So you solve these equations. So it's really basis independent. There's nothing that restricts this to any particular basis. It's a function of R prime. So you can use in any band structure method. You can use LEPW method, you can use LMTO, you can use plane waves method, whatever. You can just solve this. And then at the end of the day, once you get this quantity, we can use it in a model. Then we take matrix elements. Usually when you have a model, you work with some localized orbitals, like 1A orbitals that Nicola Marzari was talking about a few days ago. So you can take these orbitals, defined to be the maximally localized 1A orbitals. It doesn't have to be. You can also use LMTO or Gaussians. If you use Gaussians, you have a basis. And you just calculate the matrix elements of this U. So if you just want to have the on-site U, then you just take this to be on-site, these orbitals. If you want to have the intersite U, then you calculate this between two orbitals on one side and another set of orbitals on different sides. You get the interside G. So this quantity is quite independent of the basis functions. This is a depend only on the system. But the matrix elements, of course, depend on their choice of orbitals, depends on your model, how you construct your model, your choice of orbitals.
Polarization. I mean, it is like you calculated using the non-interacting Green function.
This is a non-interacting Green's function, yeah.
Okay.
The P. That's all you need for the RPA.
Yes.
As an approximation. So in principle, you could use the interacting Green's function. Yeah, you could define it as, instead of sum of occupied and unoccupied, you write it as a product of two Green's functions.
In that calculation, the size are Kohn-Sham wave functions, is it?
Yeah, so I have not specified anything about the psi, but in practice it's the Kohn-Sham orbitals. But in principle it can be anything, could be something better. Yeah. You could include the effect of self-energies, for example.
But it cannot be an arbitrary basis, right? It has to be some coming from some mean field kind of.
Yeah,
okay.
yeah. So usually from some mean field. And the usual choice is Kohn-Sham.
Okay.
What are you doing if the separation into E bands and the rest is not so easy because the bands are
That's a very good question. I will talk about it later. Yeah. We have some way of handling this problem, but actually it's an open problem. There's no complete solution to this problem. I'm not even sure if there is a solution, because if you have a crossing between the localized bands and some other extended bands, then in principle you should include also those bands in the model. So anything that you do will involve some approximations, but we have some way of handling this problem. Hopefully I will have time to go through this also. So any more question before I continue? Okay, so it's clear. So I would like to make a remark that the Hubbard U is determined by two factors. So the screening, obviously, and the choice of the orbitals. So actually when we speak about the Hubbard U, we must first define what is the model, because the U depends on what you choose as your D subspace. So if you choose a different set of orbitals, different set of D subspace, then obviously you will get a different U. So when we say U, we must also mention what is the D subspace of the thing. So before showing some results for real systems, I would like to consider a very simple model to describe how exactly we actually do the calculations. So this is a very simple model, but nevertheless it illustrates in a realistic way how we actually do the calculations. So I consider a very simple model with just 3 levels. Maybe this is the simplest I can think of. Well, maybe 2 levels would be even simpler, but it's not so realistic. So 3 levels is kind of realistic, simplest. So I have just 2 electrons up and down in the lowest state, so these are non-interacting. And we assume we have some bare interactions, V, between the 2 electrons. And now we have to decide what is our D subspace, the correlated subspace. And let us say that this is our D subspace, phi 0 and phi 1. And so this and then this, our R subspace is the phi 2. It's only one state. So our aim is then to calculate the effective interactions between these 2 electrons in this subspace alone. So we would like to downfold the system, the Hamiltonian, this R subspace, into this D subspace. We have to include the effects of the phi 2 on the screening of electrons into this D subspace. And I would also like to define this quantity here, because this quantity appears again and again. So I just write it as Bij. It's a product of two orbitals. So just write down the full polarizations. Well, in this case, we only have two excitations, two possible excitations. One from 0 to 1, so here, it's one excitations. And another one is from 0 to 2. So there are only two possible excitations. So that can B01 here, and B02. And these are just, I just put in I just use the formula for the P0, the P in this, for this particular problem. And there's a factor of 2 that comes from the spin. So I have two up and down spins. So each can be excited in the same way. So it's quite straightforward. So the PD, so what is the PD? The PD is then just the polarization within this D subspace. So then it's just this first term here. That's my PD, because that's all I have for the D subspace. And the PR is then just the difference between this and this, which is this thing here. That's my PR. So we have all the ingredients we need to calculate the screen interaction, the Hubbard U for this D subspace. So what we do? So we go back and we calculate this PR here, which is what we need to calculate the U, and we can just rewrite it in this way. Yeah. So this PRW is then the frequency dependent part of the P. Yeah. So we can write PR in this form, and the PRW here is that thing. Yeah. Just taking out the BB outside. So now we calculate the U. So the U is this equation here with the PR here. It's not the full P, because we just want to calculate the screening from the other polarization, excluding the polarizations of the model, because that is included in the model, so we want to take that out. So just the PR here to solve this. And let's say that we want to calculate, so I'm just using this quantity here. Yeah. So now let us calculate the on-site U, quotation mark, on-site U, meaning the matrix elements of the U in the, let's say, the phi 0 orbital. So this will be B00 and B00. So we call it U0000. So we just take the expectation value of this equation with respect to B00 and B00 on both sides, like this. So we get that. So let's go through this slowly. So B00, 00, V00, 00. So here we have a 00 from the left, and we have 02 from the right for the V. And the PR remains as it is. And the U now becomes 02 and 00 because we take 00 on the right side. Clear? So now we need to eliminate this 02, 00 because we cannot solve this. We don't know what that is. So we have to find out what is this. So now we take the expectation value with respect to 02 and 00 to get this an expression for that quantity. And we get we just use again we use this equation here, take the expectation value, and we get that one. So now we have an equation for the U2, U02, 00. It's the same here. And we can solve it. It's just numbers. These are all numbers now. Of course, we cannot do this for real systems, but for this model, we can do it analytically. So we get an expression for the U200, and then we just plug it in here. So we get our on-site interactions. So this is our on-site interactions. So this is the original bare interactions. I can see explicitly that this interaction is now screened by this amount here, coming from the due to the polarizations of the rest of this PR. And we can do the same exercise for the exchange. So by exchange here, quotation mark means expectation value of the U in the 0, 1 and 0, 1. You can do exactly the same exercise. Maybe I just go through quickly. So again, we have to solve for this one here. You can do that. And we get the J, let's call it quotation mark J. So you can calculate this thing. So this illustrates on how you actually go about calculate the U. So you always need to, this kind of basis is a product of two orbitals when you solve for that, because it's a two-particle quantity. Polarization is a two-particle quantity. In contrast, the Green's function is a one-particle quantity. So you need two-particle basis functions for this. So I just summarize it here. So I get the expressions for the different components. And one thing we notice is that in the case of J, we see that this quantity here is considerably smaller. So we have not put in any number, but we can kind of see this, can guess this, that this is much smaller compared to what we have for the U 0, 0, 0, 0 or 1, 1, 1, 1. And the reason for this is that because these two orbitals, 0, 1 and 0, 2, these are on different position variables. So this on R, and this is R prime. That is a product of two orbitals. And so the matrix elements of this V is much smaller compared to the case when you have same orbitals. There is a square of the phi 0 and another one. So that is why the exchange, this exchange integral is essentially unscreened. It is a very small quantity here. So it's, so this is what actually found in practice, that that the J is usually very similar to the atomic value. There's very little screening effect. J. So that is why people use atomic J. Although in some cases there are some screening effect. It's much less compared to the U. At the time. Okay. So what are the advantages of this method? So first we can get all the full matrix of the U. We can calculate any matrix elements. When we solve for the U as a function of R prime, and frequency, then we can just calculate anything we like. We can calculate the full matrix U, the whole matrix. And we have the energy dependence of U. So that also shows that the effective interactions is not a static quantity, but it's a dynamic quantity. Depends on the frequency, as you might expect when you form an effective model. You should have a frequency-dependent interaction to take into account the retardation effect from the other subspace. And then you can calculate the on-site and off-site U as far as you like. You can just calculate the matrix elements because you have the information of it in here. And this quantity itself is basis independent. So we can use any band structure method. So there is no coupling to any particular basis. like sometimes happens in the case of constraint LBA, that you make use a particular band structure method to calculate the U. So one might argue that RPA may not be good enough to describe the screening effect, calculate the U. Of course, RPA is not exact, but we notice that when we calculate the U, what we use is not the full P, but only the difference between the P and the PD, where the PD is the polarizations of the model. So there is some justification for using this kind of phase approximation, because most of the correction to the RPA should be in the PD rather than in the PR, and the PD is actually taken out when calculating the U. So this approximation may be better than one might expect at first sight. And another remark is that if we have an isolated D subspace, we really have a complete separations between the D and the R subspace, then the U should be long range, because we have removed the metallic screening from the PR. So the PR does not have any metallic screening. We look at see if I can show the picture again. Sorry. Well, anyway, let me see. Maybe I could just draw it here. So these are the R, this is the D, this is the R here. So we have removed the PD here. So there is no, it is a D subspace, yeah. So there is no metallic screening in the PR, because we removed the PD from the screening. So we expect that the U will be long range, and I will show some results that it is indeed long range. So I would like to show now some real calculations, how it works. So again, I come back to this prototype of transition metal perovskite, so for strontium vanadate, and I would like to calculate the U for this T2G band from the vanadium. So this is how the density states look like. This is how the band structure looks like. I take from this paper by Vougier, Jiang, and Silke. Sitting there at the back. You have not seen her. So this is how it looks like. So this is the band for the T2G band here, around the Fermi level. And we have this oxygen band here, and the other band coming from strontium. So this is a nice case, because the band is completely separated from the other bands, this band here. But as Peter remarked, that what happens when this band actually hybridizes with the other bands, things are not so simple anymore. But let's consider first the case when we have a nice separations between the D subspace and the rest of the subspace. So we want to calculate the U for this T2G band. And when we calculate the matrix elements of the U, we use the maximally localized 1A functions. And I think Nicola Marsari has already talked about this. Just need to skip this. So this is how the 1A orbitals look like for the particular XZ orbital. So this is the positions of the vanadium here. So this is what we call the T2G model, when we just include the T2G when forming the 1A function. So we see some components also in the oxygen. And this is what happens when we have include more bands in the model. So the 1A functions for the D becomes more localized because you have more degrees of freedom for localizing the orbitals. But let's just concentrate on this one here, because that's what we want to use to calculate the matrix elements of D. So this is the results for this is the static value. We can also calculate the frequency dependent of U, but this is just the static values. And I have plotted this here as a function of PD. So this is the simplest model then, when we eliminate the transitions between the T to G band. So we get the value of U about 3.5 here. But we could also expand the model, include, for example, let's see, this is not a good, maybe this one here. So if we include the oxygen and the EG, so we include this and this one in the model, and we have a bigger model, then the U, of course, becomes bigger because we have removed more screening from the polarization. So it becomes bigger. So actually, this picture tells us something about the screening properties of this system. So it's interesting to see that if I eliminate transition from T to G to all other, there is very little effect on the U. But if I remove the transitions from the oxygen, so oxygen here, to the T to G and the EG, then we have a very big change in the values of U. So that tells us that there is a lot of screening coming from the oxygen to P, and make a big difference between this model and that model. And we can play the same game to remove different kinds of transitions. So we can control the transitions at the very microscopic level with this key. We can choose exactly what we want to include in the model and what we do not want to include. If you remove everything, then you end up with a bare interaction here. Yeah. So let me see if I have skip some results here. So just want to show you a few more results. So this system I showed in the very beginning, so organic PET TTF organic conductors. So someone has calculated the Hubbard U for this system. Just remind you of the band structure. So this is for this PET TTF. You got a narrow band here, and we want to calculate the U for this narrow band. And this is what they found. So as I said before, that these bands are completely isolated from the rest of the subspace, and so we the U should decay like 1 upon R, because we have removed metallic screening, and indeed this is the case. So this is the bare V, just 1 upon R. So they have plotted the U as a function of R, and this is the origin. The origin of the must be. I don't remember which atom, but it's one of the atoms. And you look at as a function of R. Yeah. So we see a decay. It's a faster decay, but still it is 1 upon R, just reduced by some constant here. So that tells us that the screening is not metallic, but more like in the semiconductor. And the same here for the lights. We have a similar situation. So we have a completely isolated band. So we get the. So now coming back to the questions that Peter raised. So what happens when the bands are entangled? So this is a very difficult problem, still not solved in my opinion. So we have some method to handle this. but we are not entirely happy because sometimes it doesn't work. So let me illustrate this with cerium. So density of states, I don't know if you know cerium. There are two phases. You have isostructural phase transitions. Isostructural means that they are keep the phases, the structure the same. So this is FCC and this is also FCC, but the volume is bigger. So the gamma has a bigger volume than the alpha, but otherwise have the same structure. And this is the density of states in LDA, so LDA density of states. So you see that it is a bigger bandwidth because there's a smaller volume, more mathematical, more well-defined way. So this is another example of nickel. So you can see more explicitly the difference between the, so this is the 3D and you have the 4s band. And you can see very clearly that we have a hybridization. So again, we have difficulties in deciding what is the D subspace in this case. And again, you get quite a large variations depending on the choice of the energy window. Yeah? Yeah. Right, yeah, so I'm going to talk about that in a few minutes, yeah. Good. So this is another choice. We just look at the bands instead of energy windows. You could also label the bands. So for example, for the nickel, you might like to choose band number 2 to band number 6. But again, this is a little bit arbitrary because numbering bands is not always a good idea because you have band crossing, so you don't know how to label the band. And indeed, if you do this, you get different results. I mean, get different results. So what we do is we first construct. So this is what you're asking. So we first choose some energy window covering the 3D band. So some reasonable choice of energy window. And then we construct maximally localized one-year functions from the bands within that energy window. So again, we use the procedure of Nicola Marzari and David van der Bilt. So we have a well-defined procedure for doing this. So you construct the one-year orbitals with the 3D character. So this procedure is well defined. So there's still some arbitrariness because the choice of the energy window is still a little bit arbitrary, but it is not so crucial, I think, because you can look at how the resulting band structure agrees with the original band structure. So here is the result here. So this is the original band. Yeah. And this is the red one here is the band structure obtained from the maximally localized one-year orbitals. So you can see that there is quite a lot of similarity between this 3D band and this one here. So that's the first step. So the next step is to construct a projection operator for the D subspace. So these are then the one-year orbitals. And then we define the R subspace to be whatever is projected out from this this D subspace. Yes. So I define the R subspace to be this one here. Just remove all the D component from each wave functions. So now we can recalculate the Hamiltonian in terms of the one-year orbitals. Of course, we form block states out of these one-year orbitals. So we work in k-space. And we get a Hamiltonian separated into two subspaces. So this is the D subspace that we get from the one-year orbitals. And this R space coming from this R subspace. this wave functions here. And these two components are not zero. There is a coupling between this D and R subspace. But we approximate this by setting it to zero. We just ignore. So we get a decoupled Hamiltonian, one for the D subspace and one for the R subspace. So as a result, the band structure are completely disentangled. So you have a disentangled band structure.
Looking at the band structure at the bottom and the one at the top, I mean, the 4s band looks, I mean, for example, looks very different. Is it because of the way the top band structure is plotted, or?
Yeah, so you mean this part here?
Or actually the one between gamma to X?
Gamma to X. Gamma
so the blue line actually goes.
Yeah. So this is a kind of inevitable, yes, because you disentangle the band. So then this is, you have an S band like this, yeah, and this hybridizes with the D.
Is this because you set it to 0 here, no?
Yeah, exactly. Because we set this to 0, so there is no hybridization anymore, so you get a complete S band. And this is the D. But that is the approximation. We define the D subspace for this. So what is the measure of this? I mean, how do I know that this is good enough, or is it bad, is it good? Well, one way to check this is to calculate the fully screened interactions. So this is a plot of the fully screened interactions. I'm just looking, I think this is at the on-site component, and probably some average of the diagonal components of the terminal. Yeah. And compare the results when we use the original band structure. This triangle is the original, and when we have the disentangled band structure. So we use these two band structures. To calculate the fully screened interactions. Not the U, but the fully screened interactions. To test how good is the disentangled band structure. So you see that it's not so bad, and they're pretty close to each other. So this, the difference between these two indicate the accuracy of the agreement between the two band structures. So now using this disentangled band structure, then we have again quite a well-defined way of calculating the U, because we now have a well-defined D subspace, and we can define the PR, and we can calculate the U, and this is what we get, disentangled band structure. So we compare this with the previous results using energy window. So there are some differences, actually not so small. But this result, of course, is very much depend on how you choose this energy window. So we think that this is more reliable, this entangled band structure. So that's how we calculate that. And we could also calculate the nearest neighbor U and the Hund's J, is what we get here. So J is relatively constant across the series, typically between half, it's about half EV. So actually the nearest neighbor U is not so small, it can be about an EV or so, half an EV on average. Yeah, so there's no a little, yeah, that's true. Yeah. So, yeah, so as I mentioned before, there are two effects when you calculate the U. There are two factors that determine the U. There's the screening effect, and then there is also the localizations of the 1D orbitals. So sometimes they compete with each other. So you would expect that in the middle, the screening should be, let me see, so the PD should be the largest, so it should be large, because you have a half filling. So at this, in the middle, the U should be bigger. But there's some kind of cancellation between these two effects. So there are other methods also for handling this problem. So for example, you could use projection approach. So you project out the component from each wave functions and use it in the expressions for the polarization. So that's one way. There's another way from this paper here, where you kind of make a weighting for each of these transitions, and the weighting is determined by the probabilities of the electron residing in the D subspace before and after the transitions. So you look at the particular I here and look at the weight in this way of the D of that wave functions, and then do the same for the J. Yeah? And then you put it here. So there is no well-defined way of doing these separations. Depends. I think it is still an unsolved problem, still an open problem. So in the remaining time, I would like to show some more results, and let me see if I could just quickly show you some results. So this has been applied to quite a lot of systems now. This is quite a comprehensive study of the U for the pnictides, the ion-based superconductors. So you can look at how the U varies as a function of the family of the pnictides. This turns out to be the most correlated in the sense that it has the largest U. And I also look at the matrix elements. So this is the U matrix for this material. So one notice, so these are the 1s orbitals for the different D symmetries. These are the T2G and this is the EG. Okay, if you look at the matrix elements along the diagonal, you see quite a lot of variations in the value of U. So it turns out that these variations, so for example here it is 3, this is about 2. So it turns out that these variations does not come from the screening, but rather from the definition of the 1s orbitals. So it turns out that the 1s orbitals here is more localized than the 1s orbital here. So if you choose a wider energy window, you get a more even results. And this, I found a paper of the calculations of the U for surface, metal insulated surfaces, and I found some interesting effect. So if you calculate the U for the surface, you might expect that it should be bigger than in the bulk because you have less screening. You only have half of the bulk. So you expect a bigger U for the surface. But it turns out that for some materials, I don't remember which one here. I think it is one of the, this thing here, I think. If you calculate the difference between the surface and the bulk U, it's negative. So the U at the surface turns out to be smaller than the U at the bulk. So that's an interesting effect. And we have also done some calculations for the early lanthanides, the U for the early lanthanides. Look at the calculate this as a function of the different elements. So these are the static value. So actually we can compare with experiment. These are the experimental results. They come from the photo emission and inverse photo emissions by looking at the difference in the two peaks. The agreement is not so bad. At least we get the trend correctly. So it tends to be smaller than the experimental value. So this sudden jump here arises from the fact that one completely filled the 4F bands when we go from the samarium to the europium. So this is the band structure. And I found also So I'm just showing you some results here. These are not my calculations. So this is the U for graphene and graphite. So it seems that the interesting thing they found here is that the nearest neighbor U is very large. So it means that you don't get so much screening in this system. So it's about half actually the on-site U. Then obviously if you have such a large U, you must include this in the model. You must include a model with a long range interaction. So what else can I show here? And there is also some attempt to calculate the Heisenberg exchange parameters, although it doesn't seem to come out very well because it's not so clear actually how to calculate this J in the Heisenberg model. But anyway, you could try to do this. So this is the J of the Heisenberg model. You can kind of deduce this if you know the U and the hopping. But it doesn't seem to work very well if you compare with the experiment. So it could be because the formula is not the correct one. And in the last part of the talk, I think I would like to spend a little bit of time on the recent development related to the dynamic frequency dependence of U. So this is a very new thing. So there's some important development in the last couple of years. It's mainly driven by Philip Werner and Alexei Rubtsov. So there's a new method based on the continuous time Quantum Monte Carlo algorithm that allows us to solve the impurity problem with dynamic U, not just static U, but frequency dependent U or time dependent U. So there's this paper here by Philip Werner and Andy Millis. So I think Philip will give a talk about this. I'm not sure if he is talking about this. And this is based on the hybridization expansions. It's appropriate for strong coupling approach. And there is a complementary approach based on the perturbation expansions, correcting the weak coupling limit. So for our purpose, this method is more suitable. And there's also some approximate method by Zilka, sitting there at the back, based on the Bose factor ansatz. And I'm not going to go through this, just want to mention that this new development. So this is how the screen interaction looks like as a function of frequency for the different models. So let me take the simplest one. This is the green one, is the T2G model. So this one here, this is the imaginary part of U. So we are using a time-ordered response function. So the sign is opposite to what you have in the retarded Green's function. So you don't worry about this. You just flip this, or you turn your head down or something. This is supposed to be positive for the real, for the retarded Green's function. So this is the green one here. It's the simplest one. So that's the T2G model, and we just remove the where we have the T2G band as our model, D subspace. So you see that there's a kind of gap here. There is no transitions. This corresponds to the width of the T2G band. So the imaginary part is more interesting than the real part, for me at least, because it contains more information about the excitations of the system. So here, suddenly we have a large peak, and this large peak comes from the plasmon oscillations of the system. So collective excitations that you do not have in the non-interacting system is due to the long-range Coulomb interactions. Yeah. And there are some other structures. Also, these are probably collective excitations. So usually in the electron gas, when you have extended states, there is only one, you usually only have one well-defined plasmon excitation. So you can have several, but the main excitation is just the plasmon excitation. The main collective excitations, plasmon excitations. But in narrow band systems, you could have a more complicated structure because you have a transition from very localized states to other states, and this can give rise to complicated structure. Here, for example, you have a structure here, even here at low energy. So this thing comes from the transitions from the T2G states to other more extended states. And here I have plotted also the different U for different models. So as you go to a bigger model, you include more and more subspace. And you notice that over here, we look at the black one here. It's interesting. It's a DP model, meaning that you include not only the T2G in the model, but also T2G and EG and the oxygen. So it's a bigger model. Then you notice that the plasmon disappears. So you only have this thing here. So that is what we would expect, because this means that the oxygen electrons coming from the oxygen atoms, P, contributes a lot to the plasmon excitations, to the collective excitations. So that's why when you include it in the model, then the imaginary part of you does not have any plasmon excitations anymore. And the real part is just basically just Kramers-Kronig. There is a well-defined relations between real and imaginary part, like Vijay discussed yesterday. So this is the real part of you. So as you go from the simplest model, the T2G, to the bigger model, TP model, then the U, of course, increases for the static value. And you have this usual behavior. So the real part of U, as a function of frequency, may be negative. So you can see I have a negative value here, so attractions. So I don't know if this is a correct interpretation, but the way I think about it is that at this energy, we have a collective excitation. So the electron starts pulling in together and oscillates. So you get a positive, you have a negative interactions. It attracts, the electrons are starting to attract each other, forming a clump. So you get a plasmon. So you have this negative interactions. And then as soon as you go away from the plasmon frequency, the electron then cannot respond anymore to the field, because the field is too fast, and it starts to go into the bare interactions. That's the way I understand this picture. Let me see. Okay, I still have 5 minutes. And these are just a plot of the frequency dependence of different materials. So the point I would like to make is just that the U can vary quite a lot within the bandwidth of the model. So it may not make sense to just use a static value. So you may have to take into account the frequency dependence. There's some illustrations of what I said before for the J here. So this is for the U, function of U. And the J here is interesting because there's very little variations of the U as a function of frequency in contrast to the U. So here the U changes from the bare value here at about 25 to around 4 eV or so. But the J does not vary very much. So it's almost a constant. So there's little screening effect here. It's about 0.1 eV or so. So this is because the exchange charge has no L equal to 0 component. So if you integrate the exchange charge, it's a product of different orbitals. So it's 0. So it has no 0 component. So it's difficult to screen. So that's why there is little variations. So it is indeed justified to use an atomic value for the J in the calculations. And this is just another one for iron. Yeah. There's a bit more screening effect here, I think, for iron. Yeah. But otherwise it is similar. And this is, we get for cerium, we also calculated the U using this disentanglement procedure. So just to show you that, the U has a very complicated structure. It's not just a simple one collective excitations of plasma. So you have many, many structures. So when you look at this U like this, you wonder if it is enough to use a static value of U in the model calculations, because it varies so much. And we skip that one. And this is a recent, relatively recent calculations of the spectral functions for this one of these ion-based superconductors, where one take into account the frequency dependence when solving the impurity problem. So this calculation is an LDA plus DMFT calculations, but with a dynamic U. And you compare here the result with the static and dynamic U and the LDA. So one see quite a lot of reductions in the bandwidth coming from the dynamic U. So the dynamic U introduces further renormalization effects on the spectral functions. Now actually this effect may be counteracted when you take into account also the K-dependence of the self-energy. So this is a purely local self-energy. But it's an interesting result because it tells us that there is quite a lot of effects of frequency dependence of U. And this is how the U looks like. So for the system, there is no well-defined plasma excitations, but rather just a broad distribution of excitations across the whole frequencies. So approximately this is the plasmon frequencies, you can say, but it's not a sharp plasmon. So it's also been applied to calculate the U for the one of the cuprates here. So these are the three different D subspace. This is one band, this is three bands, and this is many bands. So the interesting thing they found is that this is the result for the one band, the black one, and this one is the blue one. The blue one or the red one, I don't remember. But one of these is the three-band model. So there's quite a big difference between the one band and three band, not surprisingly. But the surprising thing is that when you include all these other bands, there is very little difference in the U. So indicating that there is little screening contributions when you include this in the model. So it's not necessary to include all these bands. It's enough to have a three-band model. So maybe my time is a little bit up. Maybe I should give a little bit of time for questions. Okay. So just give a summary. This, and if you have questions, you can ask.
If you tell me in little detail how can I calculate U for the SRVO3 case. For example, if I start with SRVO3 with Win 2K, I will get the psi. Then I will construct the maximum localized binary function in Y90.
Yeah.
After that step, what I will calculate and how to calculate?
So you need, I guess you need a code or program to calculate the polarization. Polarization function. So this is usually available in the GW code. I think there are several codes available. For example, in the Win2K is also available, and you could also get this code from the Jülich group. It's I think it's called Specs from the Jülich in Germany, and there may be some other also in ab-init. I think you also have GW code. So you need a code that can calculate the polarizations. And from there, you just follow the same procedure as we did here. You first must define your model, define your D subspace. and then you remove that from the polarizations, and then you calculate the screen interactions. So you need a JW code, essentially, or a code that can calculate the screen interactions. So it's not a simple thing to write, of course. It takes it may take a year or two to write such a code, but there are codes available to do this.
I have a question.
Yeah.
So this lanthanum cuprate.
Yeah.
So what might be the static value of the U? Because there are a lot of calculations
Yeah.
right, on constrained LD at one point of time.
Yeah.
Right. So now you have, or people have
Yes.
been doing better ones.
Yeah, this
So-
is not my calculations, but
This
I
is
think
a
we get
published
the
paper?
similar results. Yeah.
Okay.
See, I think this is published already
Okay.
in some funny papers, not a some funny article.
Okay.
It's not in some standard journal. But we got the same results,
Oh,
essentially.
great.
So this is the value here. I don't know, I can read this. It's about 2 point something.
Okay.
2.7.
I think constrained LD was much higher, right?
I
As
think so. Yeah.
expected.
It's the usual problem.
Right.
So, yeah.
And you said the 3-band and the multi-band did not make much difference, right? I mean,
Yes.
yeah.
So,
So
that
which I
one
think is an important
interesting.
result.
Yes. Maybe not so surprising if you understand the system better. Yes.
Isn't that to some extent, I saw very surprising results. Let's say in the cuprate, you get a U of only 2.5 EV,
Yeah.
or here,
Yeah.
while in metallic nickel or iron, you had 4.5 EV. Isn't that completely counterintuitive, first of all? And second, also, if you would use a U of 4.5 EV for iron, you would get in a band structure in an LDA plus U calculation, then a huge magnetic moment, a completely unrealistic description.
Yeah.
So I don't know that the use
Is
still
that
looks
true?
strange.
If you use the value of, I thought that you have to use a value even larger than that in LDA plus U for iron.
metallic ion. No, I think as soon as you go above an effective U of 2.5,
Yeah.
the moment gets very big. So even if you use U 4.5 and J was only 0.6 or 7,
You get big.
I'm pretty sure you get a big moment.
Yeah.
Yeah.
So I don't know the answer to this, but one possibility is just you must take into account also the S in the model. So maybe this entanglement procedure is not good enough for this system. Gives too large U.
Do you know what the U in this projection method?
It tends to be too small. It tends to be too small because what happens is that you leave out some low energy screening when you do this. You don't remove completely the low energy screening in the model.
Because naively, from my point of view, these projection methods I liked the
Yeah.
most from
Yeah.
these disentangled
Yeah.
methods you presented.
Yes. But the thing is, we have actually thought about this projection method. And if you calculate the U as a function of frequency, you find that it oscillates a lot at low energy. So we think that this is not a very physical way of calculating the U. Because you would like to have a relatively constant U at low energy. But if you use this projection method, you find a lot of oscillations. Anton?
Yeah, just to elaborate a bit more on this question on cuprates
Yeah.
and make sure that I understand the point. So here the calculation that you show on the right concerns projecting on a single band in the end, or retaining also the p state.
No, I think it is, so maybe that's also one reason. That
Yes.
You only construct the 1A from this band. So
Yes.
that's a very broad 1A.
Okay, so in that
That
case,
is why it is small.
as we were reminded yesterday from Didi Sarma's talk,
Yeah.
we expect that the effective U has nothing to do with the actual Coulomb repulsion on copper,
Correct, yeah.
but is of the order of the charge transfer energy between the copper state and the oxygen state. So
Yeah.
for that number, for that quantity, a value of 2 to 3V is completely reasonable. So this I see very positively, that in fact constrained RPA seems to be able, which is not obvious to me a priori, but to capture the fact that if you downfold on a single effective band, the effective U for that very extended Vanier state becomes of the order of the charge transfer energy and not the original bare copper-copper repulsion.
It's a good comment.
I have a quick question about, so you said that once you remove the D subspace, for example, in this, the system, I mean, I guess the polarization becomes that of an insulator or a semiconductor, right? So at Q tending to 0, it becomes constant.
That's true.
Right. So in that case, I mean, if I were to do this, would it be reasonable for me to just calculate epsilon inverse for just Q equals 0? Would that give me most of the effect? Because I mean, these d orbitals are fairly localized, right?
Yeah. I think you would still have, it depends a bit on how close this other bands here to the D. So if they are far away, then I think it is okay to do that. But if it is close, then you will get quite a lot of frequency dependent features in the U.
No, I'm not talking about the frequency. I'm just saying that Q tending to 0, but I can calculate for
Oh, I see. So you're talking about the space and Q dependence.
Yeah, the spatial part. If I just, I mean, instead of R and R prime, if I just did, you know,
the Q equal to 0. So the Q equal to 0 would correspond to large R, no?
Oh, I see.
So just the opposite you want. You want the opposite.
Not, let's thank Professor Faria.